All right, guys, we're going to go on to our next set of notes for the chapter. Luckily, chapter 10, I know there's like 4 sections in the book, but I'm only required to teach 2 of them, so that's all I'm going to teach. And it's on correlation. And so the variable for correlation is R. I don't know why, but it is R. And that's the variable we're going to stick with. So correlation exists between, so a correlation exists between 2 quantitative variables. And I know I didn't really leave much space, so 2 quantitative variables. And what is, remember, quantitative are values that are I guess, variables that give you out numbers, not categories. Okay, so when the values of one variable are somehow associated with the values of another. So for example, is your wingspan correlated or related to your height? And so based off of that thing called the golden ratio that you learn in geometry, you can actually figure that out using the math that we're going to cover. So instead of looking at like one set of data now, we're going to compare 2 sets of data together, but we're not going to create, like, for example, we're not seeing if they're, we're not going to create like 2 box plots. We're actually going to graph this on an X and Y axis. If you remember from chapter 0, you guys did some work for it. With the y equals mx plus b, and you had to solve for variables and all of that. It's going to be happening with this as well, except now we're going straight into the statistics part of it. Okay, what is a linear correlation? A linear correlation is exists between 2 variables when there is a correlation. And then when you plot it, and I kind of go over how to plot it using my graphing calculator, of paired data results in a pattern that can be approximated by a straight line. Okay, if it's curved, it's actually, we're not going to worry about that in this class, which is beautiful because that's just one less thing to remember. We really care about, is it a straight line or is it curved? If it's curved, if it's bad. If it's a straight line, it's good. The linear correlation coefficient, which is R, measures the strength. Okay, strength of the linear correlation between the paired quantitative X values and Y values in a sample. Okay, so we're going to be given a sample and we're going to look at, are they related or not? The linear correlation coefficient R is computed by using the following formulas given below. Now, I will show you guys a little shortcut on the calculator how to get this, and you actually can do this a lot of ways, but I'm going to still give you guys the formula and we'll go through it. You'll just see how tedious this is. Okay, so notation for the linear correlation coefficient. So here are some notations. N is going to be the number of pairs of the sample. Number of pairs in a sample. So like this time we're looking at X comma Y and we're seeing how many X and Y's there are, not just how many X's are there and how many Y's are there. This time it's just how many X and Y's are you given. And it's like a pair. So when you graph like a line, you need to graph points, right? This symbol, which you probably have seen before, is called your summation sign. It's called summation notation. No, I'm just going to call it summation. And that means you add all values. Okay, so you're going to be using that a lot in this chapter. The next one is going to be the sum of X. So that means we're going to add all X values. Okay. And we're going to do the same thing for the sum of X squared. So we're going to add all X squared values. And we're going to do some practice problems on this. Okay. If I see something like this, what does that mean? We're going to add all X values, then square it. Okay, so this one's different than this because the square is on the outside. Okay, the next thing we're going to do, and yeah, there's a lot, is R, which is a linear correlation coefficient for a sample. And then the last one, it looks like a P, but it's the Greek letter for P, which is called rho. I'm just using P because it looks like the same thing. So I use P, which is the linear correlation coefficient for a population. Okay, and so that's really how you distinct it. Okay, correlation and population. Now, I didn't write all these values out, but you have the same for sigma of y squared, and parentheses sigma of y parentheses squared. I'm not going to write the same thing down, but again, that happens. The requirements, completely different than what you've been seeing before. So the first one, it is XRS, but it has to be SRS of quantitative data for X and Y. So it has to be quantitative data, it has to be simple random sample, but it's a point because we're looking at two data at the same time. Okay, the next one is going to be points or values. Make an approximately, and I say approximately because sometimes it isn't, make approximately a straight line. And so we want to see it's approximately a straight line and then there's no outliers. Okay, again, we're going to be going over how to graph a line on this and we'll get to go. All right, so here's two ways to do this. Again, I'm going to kind of go through this method. I'm going to do this one by hand. I'm not going to use the bottom method, but you're more than welcome to use it. So how do you find your R value? You take the number of samples and you multiply it by the sum of X times Y. Like, that's easy. No, it keeps going. Minus, you take the sum of all your X values and you multiply it by the sum of all your Y values. Okay, that's just your numerator. Your denominator, okay, is the square root of the number of samples you have times the sum of your X squared values, okay, minus the sum, or parentheses, your X values squared. And that's in your first parenthesis, or radical. Then you're going to multiply it by a square root again, and you're going to do the same thing. N times the square root of your Y squared values minus the sum of your Y values squared. And that's all in your denominator. I know it looks really ugly. That's why I'm going to teach you the shortcut method for this. Okay. Here's a good format for understanding it. It's R equals the sum of parentheses ZX times ZY all over N minus 1. And you're like, what is Z? So ZX equals the Z score for X. I'm not going to calculate that. And then ZY is equal to the Z score for Y. Now, I'm not going to use this, but it's going to be in the textbook if you want to look at it. If you want to look at that example, I'm not going to actually go over it. Okay, so let's go ahead and try an example. It's not essentially an example. It's more to like figure out what is correlation coefficient, what does it mean, and all of that. Okay, so it says it's the measure of strength of a linear correlation coefficient with R. So it says example 1, match the following 4 descriptions to the 4 scatter plots below. So you have 4 scatter plots here and you have some descriptions. Okay, I did find one mistake. There should be no distinct pattern. I know. But let's go ahead and talk about it. So it says distinct straight line or linear pattern. We say that there is a negative linear correlation coefficient between X and Y. Since the X values increase, the corresponding Y values decrease. So we're essentially looking for a negative slope. Okay, when it says negative linear correlation, that means your R is negative and slope is negative. And slope negative means you're walking downward. So which one of these shows that? And it says this one. So this is going to be your I. I'm just going to label it I. So I'm going to say the negative correlation is this number right here, which I will talk about in just a bit. But I'm going to say it has a negative slope. Okay, and it's actually a straight line. Okay, it looks like you're like, wait, it's not completely a straight line. I know, but the data, you can actually see a pattern, and the pattern is actually straight. Like you could draw a straight line if you wanted to. That was really bad. I should go through it. Okay, try the second one. Again, if you want to pause it and see if you can do it on your own, you can, or if you want to just keep going. So it says distinct pattern suggesting a correlation between X and Y, but the pattern is not that of a straight line. So which one shows that it's a pattern, but it's not a straight pattern, is this one. Okay, so it's not that a pattern of a straight line. This line is curved. Okay, so this is not a straight line. So we actually we won't be using nonlinear. That's the nice thing. We're only covering linear functions in this chapter. The last two sections cover nonlinear, and we don't even have to worry about it. So we won't do problems like that. The next one, distinct a straight line or pattern, a linear pattern. We say that there's a positive linear association between x and y. Since x values increase, the corresponding y's increase as well. So if you look at it, that's this one right here. Okay, so we're going to say it has a positive slope because it's going upward. So positive slope. And we're going to say it's also a straight line. And you're like, wait a second, it doesn't look like it's a line. Yeah, but again, you can draw a straight line through your data. Well, this one is a curved line. You can distinctly tell it's not a straight line. Like this, you can tell it's going upward. Okay, the last one, well, we kind of figured out which one it is, but it says no distinct pattern suggests that there's no correlation between x and y. And that's this one. There's no relationship or no relation. It's like asking your shoe size and your test score. Are they related? No, they're not. It doesn't matter what your shoe size is and your test score is. Okay, there's no relationship. So this is what your graph would look like. So if you see a graph like this, you're like, there is no association. Whereas this, you're like, yeah, there's an association between these two. Maybe like your GPA and your SAT scores. Maybe like there is association between that. Sometimes there isn't, but sometimes there is. Okay, what is the rounding rule? So I'm gonna say round R to at least, can anyone guess? 3 decimals. Okay, at least 3. You can do 4, that's fine. How do you interpret the R correlation coefficient using p-value and significance level alpha as follows? Okay, and so we're going to be seeing this. So what happens if your p-value is less than or equal to alpha? You reject ho. So you're going to, it changes a little, so you're going to support the claim of the linear correlation. Okay, and so this is going to be reject ho, in other words. It's the same thing as the last chapters we've been doing. What happens if your p-value is greater than alpha? You doesn't support the claim. Of a linear correlation. So you're going to fail to reject ho. Okay. So here's some properties of R. So R is always a number between -1 and 1. Okay. It's never going to be over 1. It's like a probability thing, but it can be -1. If R is greater than 0, so what kind of numbers are greater than 0? It's going to indicate a positive slope. Okay. If R is less than 0, it's going to indicate a negative slope. Think about it. Only numbers that are less than 0 are negative. R values near 0 indicate a very weak linear relationship. So like, for example, this number right here is very close to 0, so this is a very weak graph. That means that there's no relation. The strength of the linear relationship increases as x moves away from 0 towards -1 or 1. So like, for example, this example right here is -0.971. That's really close to -1. That indicates it's stronger. The strength makes it strong, and the negative means that it's a negative slope. Whereas this one is not as close. It's 0.859, which is again closer to +1. That's why there's a positive association. But the closer it gets to -1 and +1, the line or the points are closer together. So this one's not as close. That's why it's not as a bit strong of a number. Whereas this one is negative, but the 0.971 means that these numbers are closer together. Whereas this one, 0.074, you're like, there's no relationship because the points are everywhere. And then this one we don't even look like because we just say it's not a straight line. Even if this number is like, okay, that's okay. No, if it's not a straight line, we automatically stop. Extreme values at -1 and 1 occur only of a perfect line. And guess what? Data you get is not going to be perfect. Like never. Like ever. Okay, if x and y are converted to a different scale, inches to centimeters, the value of R does not change. And I want you guys to make a little note. There is no unit for R. It's just R is a number. Like R equals 0.034. Like done. There's no like inches, feet, none of that. Okay, R is very sensitive to outliers in the sense that a single outlier can drastically affect its area value. So if you think about it, because it's on strength, right? So if I had a data point right here, my line is not going to be as accurate if I had a point here now. Okay, and so this R value will actually get a little bit weaker. So if I took away my outlier, then my graph gets stronger. So outliers actually play a big factor, and that's why one of your requirements is that there are no outliers. Okay, all right, let's go on to the next thing, which is an example. Okay, it says, to better illustrate calculations of R, look at the table below, which lists 5 of the paired value data from a chapter example that have been rounded. Use technology to find the value of the correlation coefficient R for the data in the table. Okay, so we're going to go ahead and try this out. It says the data of R will automatically be calculated with software calculator. All of them should show R to be this number right here, using these numbers only. Okay, so using a graphing calculator, I'm going to write out the steps for a graphing calculator, but it says you can use StatGIS, Mini-MATLAB, StatCrunch, Excel Stat. You're pretty much, if you've used any online thing, which I know you guys have, you can find your R value with 3 or more decimal places. If you need to find your R by hand, that's fine. We're going to cover how to do it by hand at the bottom. But notice this amount of work is going to take a while. And so I actually recommend you using some sort of online thing. And if you look at this, I wrote this from the textbook. So if you look at the textbook, it'll tell it to you, or you can Google how to do it and you can do it. But using your graphing calculator, there are 3 steps. The first step is, if you remember, like when we were in class, I made you guys do this on the first day you use graphing calculators, was turn your catalogs on. Okay, so you're going to hit second, 0. Okay, so you're going to hit second and then 0. And then you're going to scroll to diagnostics on. And I'm going to do it for you. I'm just going to write it around. Scroll down to diagnostics on. And then you're going to hit enter and enter. And then it's going to say done. Okay, so I'm going to do it. I just wanted to write it out first. So I'm going to do second, 0. And I'm going to scroll down to diagnostics on. And I know it takes a little bit of time. And you don't have to do this every single time. You just have to do it the first time. So mine's already on, but I'm going to show you guys how to do this. So you're going to scroll all the way to diagnostics on. And then I'm going to hit enter, and then it says done. So just hit done, done. It says done. We're good to go. That's the first step. The next step is to, the second step is, let's go ahead and make this L1 and L2. So we're going to type data in L1 and L2. Okay, now I'm not going to use L1 and L2 because I'm going to use this for other examples. I'm going to go ahead and use L5 and L6. And again, I'm only using this because I have data stored for the other parts of the video that I want, and I don't want to retype that up. So L5, I'm going to write 5, 6, 4, 4, and 5. And L6, I'm going to write 6, 9, 3, 2, 1, 11, sorry. So I have my data in 5 and 6. So I have it in L1 and you can have it in L1 and L2. I'm going to have it in 5 and 6 because I don't want to retype the other stuff. Okay, the next thing you're going to do is you should know which one is your X and which is your Y. So for this one, our chocolate, usually the top is our X and our bottom is our Y. And that's how it is going to be for your homework. So I'm going to go ahead and I'm going to do a stat. So I'm going to hit stat. I'm going to go to calc, which calculate, and I'm going to scroll to number 8, which is ln reg a plus bx. And we're going to actually use this a lot for 10.2 as well. So I'm going to go to 8. And then for me, I used 5 and 6 because I'm not, like, I need to change it. So to change it, you hit second 1 to change it to like L1, second 2 to change it to L2. You have to clear it though. And I'm going to just hit second 5 for 5 and 6. And I'm going to go ahead and calculate. You're going to get a bunch of info. We really don't need anything just yet. We're just going to get our R value to be 0.7949, which it says should be 0.54575545, which maybe I did something wrong. Interesting. Maybe I entered in data wrong. 5, 6, 4, 4, 5, 6, 9, 3, 2, 11. Actually, I think I'm doing the exact, and I'm not supposed to. Anyway, you should get an answer. It says rounded. I'm going to assume that I'm doing it right. Yeah. All right. I mean, that's what I got. See what you get. Maybe I'm wrong with this. Okay. Let's go ahead and go on to the next part. So it says if finding R using the formula, which is not recommended, it takes a long time, but it can be done. Using the table from example 2, we're going to calculate the value from R by using the formula. Okay, so I'm going to do this really quickly by hand. Now, if you're doing this by hand, you have to create this every single time you do this. Okay, so what I did was I wrote the chocolate values vertically, and I wrote the noble ones vertically as well. So I'm going to go ahead and calculate these values first. So the first thing is the sum of the x's, meaning I'm going to add all these numbers together. So I get, let's see, 20, 34. Oh, 24. Okay, and that's my sigma x. My y is I'm going to add all these numbers up. Now I did it already, which is 31. Then I'm going to have to do this. I have to find all the sum of the squares of the x's. So I'm going to take my x values and I'm going to square them. So for example, 5 squared is 25, 6 squared is 36, 4 squared is 16, 16 and 25. And then I have to add them up. So if I add them up, I got 118. And again, I did this already, so it's kind of quick. The next one is I'm going to square my y values. So 36, 81, 9, 4, and 121. I'm going to add them together and I'm going to get 251. And the last one is I'm going to multiply x times y. So 5 times 6 is 30. 6 times 9 is 54. 4 times 3 is 12. Then we have 8. And then we have 55. And I'm going to add them up again. And I'm going to get 159. And again, this is to help us find our R value. Okay? All right, so let's go ahead and use the formula. I'm going to write out the formula once again from the first page. It was n times the square, or the sum of xy minus the sum of x times the sum of y. And I write my sums really weird. I don't know, I get made fun of a lot from my stats kids. I'm okay with that though. Over the square root of n times the sum of x squared times the sum of x squared. Yes, it does matter. Oh, sorry, this should be minus. All right, times, there we go, the summation of n times the sum of y squared minus the sum of y quantity squared. Oh, now that is why I made you guys do this chart before, because when you plug it in, it's actually a lot easier if you have these values. What's my n? Well, how many like sets do I have? I have 1, 2, 3, 4, 5. So I'm gonna write n is 5. Okay, so I have r equals 5 times, and then the sum of x and y, which you did right here, was 159. We're messing up, 159. Minus the sum of all your x's, which was 24, times the sum of all your y's, which is 31. Okay, all over the square root of n, which was 5, times the sum of x's squared. So that's this one right here. So that's 118. Minus, and then the sum of x's, so it's actually going to be 24 squared, because I'm taking the sum of all your x's and then I'm going to square it, times the square root of 5 again, times your sum of your y squared, so 251, and then I'm going to subtract 31 squared. So I kind of calculated it. So I did the top separately and I got 51. So see if you get 51 as well. The bottom, I got two different square roots. I got square root of 14 times the square root of 294. And you should try this out. I recommend you practice with your calculators just because of the square roots and the squares and stuff. Like, see if you can get this down. Like if you're using a non-fancy graphing calculator, I'm going to say you should put like 3 parentheses, like 1, 2, and then when you get to the bottom 3, and then do another one of like constantly have parentheses around this. Like see if you can get this to get you these numbers, or do it separately and then go ahead and combine it at the end. Okay, and then I'm just going to go ahead and just round to 3 decimal places. So my R is 0.795, which is what I got with this one. So I'm guessing I just typed this one wrong, but this is your answer. Okay. All right, so that's how you do it by hand. Let's go ahead and go on to actually looking at some hypothesis testing, and then I just do a bunch of examples. Well, not a bunch. So we're gonna let P, which again is your road. Look, it's a funny P. Okay, it's going to be a linear correlation, coefficient, of the population. So remember, we use like mu, we use p, we use all of that because it's a population. So your ho is always going to be rho is equal to 0. Remember, it's always equal to 0. It's the same thing. Again, if you want to write a p, you can. But this is saying that there is no correlation. There's no relationship. Your ha, depending on what it is, we're going to say ha is either going to be not equal to, less than, or greater than your 0. So there is association, or there is correlation. Okay, now if you're doing this by hand, we're going to be using data that we don't know the population for. So we're going to actually be using a t-test for this. And the formula is t equals r over the square root of 1 minus r squared all over n minus 2. So your degrees of freedom in this problem is n minus 2 now. It's not n minus 1, it's n minus 2. And then you use TCDF to find p-value. Just remember, degrees of freedom is in your TCDF anymore. You're going to be using that. Now notice you're like, wait a second. Your R value. Yeah, if you use this formula, you're going to have to do all of this work just to find your R value, and then you have to plug it into your R to find it. So when I'm doing this by hand, quote unquote, I actually know my R value. I'm not going to calculate all of that by hand. I'm just going to use a calculator for that, or an online thing. Okay, if you're using a graphing calculator, you're just going to find the test that says linear regression t-test. And there's a lot of information you have to write out. I'm not going to make you write out everything. I'll tell you which ones to write out. You could write out everything you want if you want to, but this is what you would want to write out. You want to tell me where your x is, so you can write out like the list number. Your y, tell me what list number you're using. So same thing as before. So is it in L1, is it in L2? You're going to tell me what your row is. Is it not equal to? Is it greater than? Or less than 0? So which one is it? Again, write it out. You're going to tell me what my t value is. You're going to tell me what my p value is. You're going to tell me what my degrees of freedom are. And the last one that we haven't done is you're going to tell me what your R is. And again, that just makes it a lot easier to see your work. Okay? So, hypothesis testing. Two-tailed, right-tailed, and left-tailed. Again, as the same as before. So if it's two-tailed, what's my ho? Well, it's the same. Rho equals 0. My ha, if it's two-tailed, is that rho doesn't equal 0. And my graph would be, again, exactly the same. I like this because it's like literally the same thing as before. My right-tail test, my ho, what is it? It's still 0. And my ha is that it is greater than 0 because we're going to the right tail. And I know I'm kind of breezing through this because we've done this so many times. It's just this part that changes. All right, last one. My ho is still p equals 0. And my ha is p is less than 0. Or rho is less than 0, and it's a left tail test. Okay. All right, you guys ready for an example? Because I am kind of... Oh, I already did this side. All right, let's go on to the next page. Last page for our notes. Well, this one and the back side of this. Okay, it's using the entire chapter example. Calculate your R value for chocolate consumption and Nobel laureates. Is there a linear correlation? Using a significance level of 0.05, is there sufficient evidence to support that the claim that there's a linear correlation between chocolate consumption and Nobel of laureates? I don't even know how to pronounce that. I hope I'm planning this out. All right, so we're going to go and do an example completely. Okay. So this is what I was talking about, is I don't want to have to re-enter data because I typed this in L1 and I typed this in L2 and I don't want to retype it. I already did it before, so let's go ahead and let's not do that. Okay, so first thing I'm going to do is I'm going to type this out. So typed it out, so I hit edit, and in L1 I typed up the 4 pieces, the chocolate data, and in L2 I typed this up. So you might have to pause the video and type this up if you want to. Okay, if you don't want to, you kind of want to listen, that's fine. So the first part is state. And I'm going to write a little smaller just because I didn't give myself all of this. I should have, but I didn't. What are we using? We're using row because we're looking at 2 pieces of information. Okay, so how do you know you're using row and not like mu or anything? We're looking for a linear correlation because that kind of gives it away that you're using row. So we're going to have P equal linear correlation between, I'm just going to write chocolate and the Nobel laureates. I don't really know what this question is even saying, but there you go. What's my ho? Well, it's p equals 0. My ha, well, okay, if I read this problem, it doesn't say if it's less than, if it's greater than, or anything like that. So we're going to say that rho is not 0. Okay, if it said greater than, then we would say greater than. If it said less than or smaller, then we would use the less than symbol. But since it doesn't, it's a two-tailed test. So our state, let's go ahead and do a plan. Okay, so first of all, we have X and Y and their quantitative data. We just don't know if it's an SRS, but I'm assuming it's an SRS because this is a problem from the book. So I'm going to say SRS, and X and Y are quantitative data. Okay, now the second step is that you have to graph it and show that it's a line. Okay, so that's the first one. The second one, we're going to have to graph it. Okay, so how do you graph it? Okay, well, everything is in L1 and L2, so it's kind of just like doing a box plot, except we're going to do a linear regression. So you're going to do the same steps. So my L1 and L2 are there. I'm going to go ahead and hit second stat plot. So I'm going to hit second stat plot. And we've done this before, and we turned the first one on. But remember, we always use like the box plot. This time you're actually going to keep it on the first one, which is the linear regression. And then just kind of make sure your X lists and Y lists are L1 and L2 or wherever your data is. And then so like really what's changing from the last step to this one is we're not using box plot anymore. We're using an X plot, and then we're going to hit zoom 9. Okay, so second stat plot, check the one that's like a scatter plot, and then you're going to hit zoom 9. Okay, oh, sorry, I didn't erase the equation yet. Okay, zoom 9. So you have something like this, so I'm gonna go ahead and sketch it. So it's a sketch, it's not perfect, but again, I'm gonna try to do a good job of it. Okay, now here's my question to you. Does it look like a straight line? Does it show outliers? Okay, so if you do this, I'm gonna say this looks kind of like a straight line. And I'm going to say may have outliers. We don't know yet. Like, we could say, oh, that looks really off or that looks really off. But, like, overall, it looks pretty straight. Like, it looks like a straight line. It doesn't look curved or anything. It's pretty much straight. It's a weak graph because it's not all, like, perfectly lined up. But it should be okay. All right, so that's our first part. And then the third part, I already did it, but may have outliers. Sorry, I should have done that. May have outliers. Okay, so that's our state, our plan. Let's go ahead and do it. So I'm going to, again, do it by hand and by calculator. But what I mean by hand is your R value should already be given. And you're like, how do you find your R value? So to find your R value, you kind of did what we're supposed to do before. You're going to go to, we've kind of done this, I think. Did we do this? We're going to go ahead and go to stat. And you're going to go to calculate. And you already did this. We're going to scroll down to number 8. And we're going to do line reg. And it's the a plus bx. And we're actually going to use this a lot in the second video. And you just have to change this to L1. I have to change this to L1 and L2. And I hit calculate. And I'm going to find just my R value. So my R value is 0.801. Okay. Again, you have to, and if you don't want to do it like this, you actually have to do the work we did with the chart with all of these values. So it takes a while. Okay, so let's go ahead and do it by hand. So if we're doing it by hand, we're going to go ahead and use t equals r over the big square root of 1 minus r squared over n minus 2. Okay, so our R value, our R value is 0.801 over the square root of 1 minus 0.801 squared over n. And n is however many numbers there were. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. There's 23. So I'm going to write n equals 23. I should have done that earlier. So we're going to say this is 23 minus 2. So we're going to go ahead and calculate that. So I'm going to do parentheses, 0.081, close my parentheses, over another parentheses, and then I'm going to do square root of parentheses 1 minus 0.801 squared. And notice it's not squared of the parentheses, it's squared of just 0.0801. Otherwise, I would have the squared on the outside. divided by, notice I'm still in my square root, of 23 minus 2, which I can do that math in my head and get 21. And so my t-value is 6.131. Now that's my t-value. I have to find my p-value, so I'm going to use TCDF of, and since this is positive, I'm going to think that's my lower. My upper is 1,000, and my degrees of freedom, again, is not n minus 1 anymore, it's n minus 2. So I'm going to write 21. So this is my lower, my upper, and my degrees of freedom. Now, since this is a one-tailed test, I have to multiply this by 2 for two-tailed. So I'm going to do distribution TCDF of 6.131. 1,000 degrees of freedom is 21. And I'm going to multiply this by 2, and I'm going to get 4.398 times 10 to the negative 6, or really close to 0, if you want to think about it. Okay? That's if you're doing it by hand. Let's go ahead and do this by calculator. So if we're doing this by calculator, we're going to go ahead and write the test we're going to do. So we're going to do a ln reg t test. Okay, so I'm going to go ahead and go to that. So I'm going to go to stat test, ln reg t test, which is F for me. And I'm going to go ahead and write what I'm supposed to. So my X was in L1. My Y is in L2. Frequency, I don't have to write out. My rho, which is B, we don't have to worry about the beta. We just have to worry about rho is not equal to 0. And I don't have to worry about the equation, and I hit calculate. So I'm going to write out what I have. So my t value was 6.123, which is really close to what I had. My p value is 4.477 times 10 to the negative 6. Again, very close to what I had because this is really close to 0. And I want to write my degrees of freedom to be 21. If I scroll down, I do want my r value, 0.801. And if you look at it, we got the same answer for 0.801. So if you're doing this by hand, or by calculator, you don't actually have to write this part out. You're just doing it all at once. So it'll calculate it for you. All right, last part is conclude. So I'm going to write p-value is 4.398 times 10 to the negative 6, or you can write approximately 0 because I know some of your calculators do that, which is actually less than or equal to alpha, so we reject ho. There is sufficient evidence that there is what? A linear relation, there is a linear relationship between chocolate and noble. I'm not going to write it all out, but there you go. Okay, so remember, 0 means that there's no relationship. This means that there is a relationship. So there is a relationship because we rejected the ho. Okay, our next part is going to be interpreting our explained variation. So if we can conclude that there's a linear correlation between x and y, we can find a linear equation that expresses y in terms of x. And we're actually going to see this equation in the next section. That equation can be used to predict values of x for given values, or at y for given x. So meaning you can plug in numbers into your equation. The value of r squared is the proportion of the variation in y that is explained by the linear relationship between x and y. So if, for example, this value 0.801 is your r value. How do you find your squared value of that? You square it. So it says, go back to example 3 and answer the following question. What proportion of variation in the numbers of Nobel laureates can be explained by the variation of the consumption of chocolate? So every time you see variation, you're going to find your r squared value, which if I go ahead and do 0.801 squared, okay, I get 0.642, okay, which is approximately 64.2% if you want to think about it like that. So if you want to use a little sentence frame, I didn't really write it out, but we can say we conclude that 64.2% of the variation and then you're going to write your y variable, but I'm going to go ahead and write it out. So in the number of Nobel laureates, laureates, can be explained by a linear relationship between, and then you're going to write your x and y variables. Again, I'm going to write this out in terms of this one, but that's what you would fill in. So it can be between the chocolate consumption and Nobel laureates, number of Nobel laureates. Okay. All right. Now, I do want you guys to think about the last part, or this is the last part of the notes, is remember, correlation does not imply causation. So things being related to each other doesn't mean that one causes the other. So like if I was saying if your arm span and your wingspan, are they related to each other? It's not implying that they're caused by one and another. So like knowing your wingspan, you don't know if you can if it affects your height. Like they don't relate to each other in terms of that. Okay, they're not cause and effect. It's more like are they related or not, and it has to be like one set time of data if you want to look at it like that. Okay, so we're gonna go through one more example. You might have seen this example before in our notes from like chapter 1, and I picked this out from your book because I thought it would be good. And it says, listed below are the number of registered pleasure boats in Florida, if you remember that from the first chapter, and the number of manatee death fatalities from encounters with boats in Florida for each of the several recent years. The data from set 10 of manatee deaths in Appendix B. Again, I took some data. Is there sufficient evidence to conclude that there is a linear correlation between numbers of registered pleasure boats and the number of manatee boat fatalities? So again, linear relation, so you know you're using the linear regression. Okay, so first of all, the first thing you want to do, and again, you're going to do this by hand or by calculator, is you're going to type this data in. Now for me, I already have, again, typed this out in L3 and L4. If you need to pause it, you can pause it out, but let's go ahead and do the state. We're going to do it all, so state. So we're going to let rho equal a linear correlation, and what are we relating? A linear correlation between pleasure of boats. If you remember like the first chapter we did this, and manatee fatalities. We're doing the math finally from it. Okay, my ho is that there is no association, and my ha is since it says is there evidence to conclude that there's it doesn't say less than or greater than, so we're going to say rho is not 0. Usually it's not, but you might see it. All right, let's go ahead and do the plan part. So for our plan part, well, I took this from your book, so I'm assuming it is. I'm going to say SRS, and both X, Y are quantitative data. Okay, if it's not quantitative data, well, we can't even do the problem. So this is quantitative data. If I had like a color of boats and it went blue, black, red, green, black, red, that's not quantitative data. You can't really quantify that. This is quantitative data and you're good to go. The second step is to graph it. Okay, so it doesn't matter if your sample size is a certain number, you actually do have to graph it. And how do you graph it? Again, it's the same thing. You're going to do second stat plot. Instead of box plot, you're going to go ahead and do the fourth one. And I'm not going to use 1 and 2. I'm going to use 3 and 4. Again, I already typed it in, and that's why I'm doing it. I'm going to hit zoom 9. And I'm going to go ahead and graph this. And I'm going to say 1, 1, 2, 3, 4, 2, 2, 2, 2. Does this look linear? All right. So this kind of gives you an idea of, is this going to be linear or not? And you can kind of be like, it's not going to be linear, but we have to prove it. We can't just say the graph doesn't show linear, so it's not going to be. But I'm just going to say not, that's actually right, doesn't appear to be linear and shows outliers. And we're still going to do it all, but what are we going to say at the end? We're going to say that it might not be reliable because it's not matching everything. Okay, so let's go ahead and do the do part. Okay, now if you're doing the do part by hand, you're gonna have to find your R value. I'm gonna do the do part first by calculator this time because it tells me my R value and then I can use that for my hand part. So if I do this by calc, I'm gonna say what test I'm gonna use. So I'm gonna use a lin reg t test. And then I have to type in where I'm typing in my data. So stat tests, I'm going down to F. And then this time my X is going to be in L3. And my Y is going to be in L4. My row is going to be not equal 0. I'm gonna hit calculate. And again, I really don't need all the information. I need T, which is 0.960, P, which is 0.369. I need degrees of freedom to be 7. I'm just reading this off. And then if I scroll down, I'll get my R value to be 0.341. Okay. If I'm doing this by hand, I have my T value, which is, I guess I can write out the formula, R over the square root of 1 minus R squared over N minus 2. So my R value, again, you would have to do your stat, calc, linear reg to find your R, just find your R by hand. I already did it because I used this. I'm gonna use 3.341 over the square root of 1 minus 0.341 squared over N minus 2. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 minus 2. I'm going to go ahead and calculate that. So parentheses 0.341 divided by, close it, radical, parentheses 1 minus 0.341 squared, close it, divided by parentheses 7. And you get 0.960, which is what I had here. Great. So I know I'm kind of doing this right. The last part is TCDF. Now since this is positive, I'm going to go positive, so 0.960 to 1,000. And my degrees of freedom is 7. So this is my lower, my upper, and my degrees of freedom. And I'm going to multiply this by 2 because it's not equal to. I'm going to go to TCDF. My lower was 0.96, upper is 1,000, degrees of freedom is 7. I'm going to multiply this by 2. So you get 0.369, which again, that's what I got for this number, so I know I'm doing it right. Okay, so my last part is conclude. And I'm going to say p-value is equal to 0.369, which is actually greater than alpha. So what happens if it's greater than alpha? You fail to reject Ho. There is no sufficient evidence that there is a linear correlation between pleasure of boats and manatee fatalities. Now, since my plan didn't check out, I'm going to write since the graph isn't linear, the data might not be reliable. And the reason why I'm writing this out is because not all of this checked out. If all of this checked out, I don't have to write this sentence, but since this didn't check out because of the plan part, we have to write the sentence at the end. Okay, and that is the end of the first section.